Mutual Line, and I would like to talk about one project that my team and I did in for a data science project in Gruppo Mutual Line. Just a couple of words about Gruppo Mutual Line. You may know it because of the websites like Mutual Line or Segugio, where you can compare mortgages or loans or insurances. But this is just one half of the company. The other half is the BPO division that I work for, and is the business process outsourcing part of the company. So business process outsourcing for us means that we manage for our client the complex processes that are behind their financial products. For example, in numbers, we can say that we managed 75. Okay. So 75,000 mortgages and 100,000 loans or insurance claims for our clients. In practice, this means that if you take the example of a mortgage, of course, it has several steps behind it to obtain your mortgage. So we can do the credit assessment part, the anti-fraud part, even the property evaluation, or even the customer support. And this can happen for several services, for several companies, so also for loans, and every single service, every single client has its own processes and business views about its products. So these are actually very complex because are financial stuff. Sort of, there are banks behind all this, and one of the main reasons why it is complex, because in a mortgage, for example, several actors play the same game. So there's the notary here, the final customer, of course, the bank, but also the company that does the property evaluation. And one of the central point of all this is that all these people need to talk to each other. And for example, they send emails to each other, and being in the middle of often of all these processes, we receive thousands and thousands of emails that we need to at first at least organize. So this process actually of we receiving emails should be and must be actually very optimized, because it can be very time consuming if you need to do sorting, and you need to do sorting because every email has to have its own pipeline, like go to the office B or to the process whatever, and to some people forward to the other. So the first step in all this email pipeline is send the email, work the email as you should, or send the email to the people you should, and or even archive the email the way you should, because you being involved with financial stuff, you have to be able to get the email back also after years. So everything should be archived correctly. So sorting. Everything almost everything in the company happens in a company software that is developed by our team of developers inside the company, and this process of sorting happens there on the company software, where people, as part of their job, read the emails and assign labels to them so that they can keep on working, or other people can keep on working on the same emails. So, this is where we wanted to give our contribution, because of course, classifying emails is a bit boring and time consuming at the same time. And of course, it can be in some way automatized. So as a data scientist, of course, we read sorting, we read classification, and we immediately think about machine learning. So yes, we're going to do machine learning. Yes, we're going to do neural networks and all these other fancy stuff. And with the goal of helping this process of sorting things. So let's look at the problem more closely. So what should we predict? What should we classify? Of course, we have emails, but people do not assign just one label. They assign 3 labels. So we have 3 targets, and each one of them class. So it's not a binary classification problem, it's not even a multi-class classification problem, it's a multi-output, multi-class classification problem. So, okay, very interesting. We have the target, now let's look at the data. We have emails, so we have text. All our features are mainly text. Sender, receiver, subject, and all, yes, and some other more particular features, but yeah, mainly text. And, of course, the company is not born yesterday, was not born yesterday, but 15 years ago, so legacy database, of course, for the emails stored in, yes, we're going to talk a bit more about this later. So, in principle, as a data scientist, we know where to get the data from, we know our goal, and we can start with our exploratory analysis and so on. But actually, we need to ask ourselves one more question, that is, whatever we are building, how are they going to use it? So the first thing we did actually was to go to the person that are classifying emails and just sit next to them and look at what they do. And it turns out that an automatic classification, a completely automatic classification, is unfeasible. We cannot do it for mainly two reasons. One is the legal reason, that is, for some of our client, for some services, there must be always one person that is responsible for every action that is performed on the full process. And the other is some operational reasons related to the workflow that these emails must follow. So, okay, no hard classification, avoiding completely this piece of work, but we can make suggestions. So instead of looking down and scrolling for among many classes, we can just restrict the possibilities among the most probable classes every email should have. Yes, and this is exactly what we thought. We discussed it with the developers of the software, and this is what we had. So 3 drop-down menus where people just scroll down looking for the right class, and our point was, let's substitute all this with something much easier to use. Do not look for your class among 50 classes, but just show the first 3 probable classes for every label. So each row is a label you should assign. Mm-hmm. Okay. Yeah. So each row is a label, and the classes can be something for each label. And if our model is confident enough, we could even pre-select the right class, so that the person reading the email just reads the email and then press the OK button if he agrees or she agrees with us. Okay, now we kind of drew this problem in a more formal way. We know what to do. Let's go to the data. We said legacy database. For us, legacy database meant restricted and inefficient access to data. That is, in other words, that we make there our complex analytical exploratory queries. The rest of the company just shuts down, because every software is built on top of this central database. So we simply cannot do the analysis there. Okay, bit of a problem, but talk to the right people, like the database administrator and system integrators, and easy solution actually. Just export the full history of all emails you ever had in Grupo Multi-Online somewhere else in some other, whatever format you like, but probably the most simple one is the most manageable one. So just a JSON with the data you have about these emails. So here you have your targets. So we should predict these classes here, and then all the other features like the text, subjects, and the sender, and the email inbox, or the date time at which the email was received, and so on. Very good, because now we have our place where we can do our fancy stuff without any impact on the rest of the company database. Nice. Let's go to the model, or better, to the exploratory analysis and blah, 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 that we are not going to cover now in this talk. But, so yes. Let's see what we have. We have 3 targets to predict that we need to predict at the same time because they are not independent from each other. Features are mainly text, and because they are text, you may want to try different strategies on preprocessing, on whatever you want. And also, very interesting point, that data is a lot of data, so it cannot fit in memory. You cannot just simply pandas.read JSON and that's it. In particular, more than 3 million emails, and emails can be very, very long, like 10% having more than 600 words, and also words can be very, very different. The Italian vocabulary doesn't have 1 million words, of course, but conjugations, proper nouns, company names, abbreviation, I mean, you can find whatever you want there. Typos, of course, lots of it. And yes, so interesting point here. And one more point, of course, it was needed yesterday, or in other words, I want it now, or all the other business sentences you may know very well. That if you want to say in a more right way, the first viable solution should be available as soon as possible. And if you want to make improvements later, do them. But of course, once the solution is in production, you cannot shut down your application, right? So do whatever model you like, but if you need to switch the model, you cannot shut down the application, for example. And also, of course, you're a team, so if this works and is in production, of course, when you want to improve this, you will be doing so many other projects that you won't have time to actually really improve this. Yes, so this is what actually we saw at the beginning and decided to focus on before focusing on the model. So instead of building the model, let's build a training architecture so that we can, a very simple one, but so that we can run experiments and then deploy these experiments whenever we want. So if we look at the problem from what we have to do from a bird's eye, we have some features that something transform into targets. So nothing more. Whatever you want, in particular our neural network, our reading the data happens here. So the first principle we thought it was very useful to apply is decoupling. So let's just split things. So something that reads the data and then whatever model you want is just fed with this data that is read by this model. So that, for example, the batch by batch strategy that you need to implement because the data doesn't fit in memory happens here, and the model just doesn't care. So you just need a model that you can train incrementally, like neural network, and you can write your generator here. And here also can happen all your preprocessing part, the tokenization part, the application of pre-trained embeddings. Whatever is fixed, you can apply it there. Whatever is actual training happens on the other side. Having those two parts decoupled mean, of course, that you can, for example, change one strategy here without any impact on the other side, and so on. So if we look at the data generation part, we know that we are going to use neural networks because, I mean, it's text, we need incremental training, so we need freedom to try different things, so okay, easy solution. Keras, another easy solution. You may know this framework for neural network in Python. And Keras has a very useful classes inside the utils modules, like the sequence, that is nothing more than a generator plus, where that you can subclass, like in this case, and you need to provide just a dunder getItem method that needs to return one batch with your feature. So you need to provide the number of course, the batch size and the number of batch you're going to have with all your data. and this is the dunder-len method. But the dunder-get-item method, for example, read the data from the JSON, whatever, and then outputs the features with the target, because we are training, or without the target if you are at predict time, of course. But there, now, here, you can, in place of these 3 dots there, you can do all the text processing you want batch by batch, because this is going to be cycled on by the model when you fit the model. And so punctuation removals, filters, regex, substitution, whatever you want can fit in here. And also, for example, the use of the vectorization of your text in numbers. So turn frequency, inverse document frequency, word-to-back embeddings, if you have them pre-trained somewhere else, you can apply them here, batch by batch. Okay, we decoupled the data generation part and the model part. One more decoupling step. You want to decouple the training part from the model itself, like that if you want to change completely the architecture of your model, you are not actually changing the way you are training it. Maybe the same optimizer, or maybe the same code, actually. So let's just build something where you can define your model somewhere else. So changing the architecture, changing the model is just writing one more function in your model modules. So this is a training, and here I'm doing the model.fit generator that automatically calls my data generator something that does all the stuff, completely abstract from this script here. And the model is nothing that an object that I instantiate here, passing some configuration, but the model function itself, that is the function that creates the model. So this Keras object that I fit here is something I can import dynamically, just specifying the name on a configuration. So I write my create model function in an external module. I write in my input configuration file the name of the module, and this works without any other change if you want to completely change the model itself. And the model is built with the Keras functional API, where you, in this simple example, define your input tensors, that in our case are text, subject, sender, receiver, in our example. Of course, at some point you want to concatenate them, pass them to some hidden, fully connected layer, and then output your 3 softmax activations, layers with activation, so that you have your outputs. And at the end, my beautiful model function, return the Keras object. Now you want to apply CNN, or I don't know, whatever you want to implement, and you just completely change here, and the training works, and the data generator works, and I have to change nothing about my code, but this function and the configuration I'm sending when I press the train button. Okay, nice. So now we have something we can play with. So let's do something. Of course, we have to. The first thing we should do is to find a way to transform the words in numbers. Of course, neural networks understand words, not numbers. Many ways. One of the simplest one is the TF-IDF vectorization, if you want, where the term frequency is just this bag of words stuff. You just put on your columns the unique words you find. So the 1 million word, if you want, or less, better. And then every row is an email, and then every value is, for example, the presence of these words in this email, or the frequency of these words in this email, or in this case, this is term frequency, or the frequency of this word in this email, times the inverse of the logarithmic frequency of this word in all the documents you have. And there are many other ways. The two most useful one and simple one are this one. So, okay, this happens in the data generation part. So the inputs we saw at the beginning just are being fed with the TF-IDF vectors that we can concatenate and we can and we pass to the hidden layer. So this is just the graphical representation of what we had with the Keras. Yes, with this My Beautiful Model. Okay, this is My Beautiful Model, just with a fancy drawing. Some more layers. Okay, no worries. Just write another function and that's it. You want to change, maybe you want first to concatenate all the text and then make the TF-IDF. No worries, that's the same. All the data generation models can take care of it. Or you may want to not to vectorize things with TF-IDF and blah blah blah, but use the word embeddings. So assign to each word a full vectors with dimension 100, let's say. And this vector, you hope, because other people train these models on the full dump of Wikipedia, for example, that represent some sort of meaning of these words, so that these vectors, with this vector you can do something like king minus man is queen, something sort of that, so that the vectors actually represent meaning of the words. Again, no worries. If you have pre-trained vectors, you can put this word in the data generation part, or you can even train this vector in the actual training with your embeddings. So you train not the word-to-vec representation of Wikipedia, you train the most useful representation of this word for your problem. And of course, for every email, it can have many words. Here you have one vector for every word. So while here start with a vector, and here you should end up with a vector, here you have a matrix. So one vector for each word. So you need something to squash everything to one single vector. Okay, let's make a simple average, or make a max pooling, or sort of sum everything up. Many strategies here, so you can try different ones. You may not want to train your embeddings in the network because it becomes also very slow. I mean, you have to train many other weights in the network. So let's use pre-trained word-to-vec that we tried, and we tried also so pre-trained vectors on the Wikipedia dump that we fine-tuned on our training set. And yes, the important point here is that whatever you try here, everything reduced to write a function, write the model function and something in the data generator part. But everything else, all the application we're going to build on top of this, it's the same. You're not changing anything else. Oh, okay. This was interesting. We discovered a paper about smooth inverse frequency that I don't know if you ever heard about. That was interesting because it actually addressed an issue that we weren't so satisfied with. That was this squashing of matrix in a single vector. That is, a simple average could be not. I mean, you may be not very satisfied with that. So the smooth inverse frequency was very nice because it's a weighted average of these vectors based on the term frequency of the words. So the average there is weighted on how many times that word appeared in some other documents or in that email. That was very nice, easy to implement, and yes. So many experiments. So what we discovered is that actually, in our case, the use of word and vec things gave slightly worse results every time. But one case, the one of Sif, that we liked. But the point was that every more complex model we built actually was not so better or even worse, that the most simple ones, like TF-IDF and just fully connected layer. And this was our accuracy on the three labels. But if you remember the problem, these are, of course, indication of how good you were in training a model, but the true point here is how many times people will find the right classification in my box. So our accuracy here is saying that 98% of the times the person reading the email will find the right class there. So, okay, we are all very happy and we can go on in building the application. Yes, this is what I was trying to say, yes, until now. So the point was that we were able to run all this because of the coupling approach and make every experiment as easiest as possible, because at the same, running a new model here just reduced to change the configuration. That was very nice because everything was already in production and you had so many other things to do. Yes. Okay, now we are at this point here. We have our beautiful Keras model that we study and decide at some point we have to communicate with our application. Well, okay, let's talk with the modern web standards. Just exchange the most simple and easy and manageable unit of data, that is, you send me the email and I send you the predictions. Okay, Flask framework, one of the simplest and lightest web framework for Python. The very statisticians among you may wonder what it is. It's just an object, let's say, an object that you run with the up.run, and this just is up and running, so it's a process that keeps going. And if you define functions that return strings, let's say, or JSON dumpable stuff, you can expose this function for your browser, for example. Like if once I .run my Flask application, I can go to the browser, point to the IP address of this machine, /predict, and I get 0 as a string in my browser. Of course, they don't need the browser, they need the request method, of course. Not everybody of you may have worked in Flask, but many more of you have just requested something to the Google API, for example. So this is what they are going to do, the developers of the company software, just make us some request. In our case, we don't have to output 0, we have to output our predict method applied to the JSON we are sending us, and just JSON dump our result so that they too get the JSON. So that was nice, easy, from 0 to my model. And so we built all this stuff here, and we discovered that it was very fast, so enough to be production, good for production even for them, because there is this symbolic threshold of 200 milliseconds above which people feel that the web page is slow, and of course people working with the company software don't want that. So okay, we are good, nice, but we are in production. So it means that we should always up and running. With always, it means that whatever happens here, even, I don't know, someone that by mistake shuts down the machine, this should keep on working, right? But of course, we wanted something more. We wanted to be able to change the model, I mean, whenever we want. Again, you go to your system integrator and say, oh, okay, what we can do? Easy. Let's use 2 Flask servers, and put before that something else that just load balance your traffic. So the company software do not call us, call someone that redirects the request to either this guy here or this other guy, and then I answer back to this, that answer back, actually, I answer back to the software. And this HA proxy guy there can know if my application is available or not. For example, I can write another very simple Flask method that just returns up with the 200 HTTP status of OK, success, if a global variable is true, or off, down, whatever, if this is false, and also provide a switch method. So when I want to deploy something, I go to my browser, I go to the switch method, shut it off. The application is perfectly working, just HA proxy now knows that it has, it cannot forward request to me here. Okay, I can shut down my application, change the model, and make the application, and restart the application, and put it on again, and then do the same on the other server. So easy, this can be automatized. With that, it's very easy when you, yes, it's very easy actually. And okay, so high availability, and also scalability, meaning that if the traffic is growing, just add more Flask machines. Of course, again, everything is virtual machines, so the system integrators have the template of these machines. You need some more power. Okay, so just turn on one more of these servers. And if you like Docker is the same. I mean, production worked before Docker existed, so this is whatever you like. Nice. Okay. One point. We have this beautiful application, and the business point here now, we have prediction, is how do we measure if everything is working or not. From our point of view, of course, everything works if our model has good accuracy. That may change in time, however, if we want to say a big word, is concept drifting. But also just there's one more label or one more class in the labels. Everything could happen. So we need a way to monitor this in real time. But at the same time, we need something to monitor this in real time, and we know that the data generation process is there, meaning that when I send back my prediction, there is one person that pressed the OK button, and in this moment, that person there knows what the true level is. So the software can just send this answer back to me. Not much of a effort for the software, and lots of results for me. So yes, I send the prediction, they send me back after the OK button another JSON with the notification where they tell me you gave me this prediction, the person said this other class, so wrong, shame on you. And in this way, we have something that we can use to make performance monitoring in real time, but also now you have the data, you have the new data, so you can even collect in this way instead of this other way. Or, I mean, online fine-tuning. Have fun with that. One little problem, nothing must interfere with the application, meaning that we could be doing something heavy, maybe, I don't know, with monitoring or fine-tuning here, and we cannot do it here, actually, because we cannot assume, we don't want the risk that more workload here would spoil the 100 millisecond of time we were giving to the application. So in some way, we should send our data somewhere else so that the workload, again, is decoupled from the main application. But if everything is synchronous, and it's an API call, so if the company software calls me and I send the data synchronously with another web API here, it means that the guy there must wait that here the work is finished. So again, the coupling So let's put our work on some middle layer that is a queue, and this takes care of all the load, all the data I send to him. And on the other side, I put something else that just reads from the queue. In this way, I completely decoupled the data producer part from the data collection and data whatever you want to do part. In our case, we can do the monitoring without even knowing who the producer is, or collect new data or online training without knowing how many producers are going to do that. So this Rabbit here, this queue system, you may know Kafka or other queue system, implementing an asynchronous communication very fast, of course, allows you to be real time and at the same time completely scalable, decoupled from there is no real communication between the consumer and the producer, and fault tolerance and scalability, as we said. In our case, for example, as we said, we could make here the new very small process that just consume the data from the queue and pre-process them in some way that we like the first massive JSON we saw, and store it in some other database, and exclude this part of the first part of this process. But again, if you remember, the question was how do we measure success? So we have our notification with the right prediction, and if everything works as it should, actually the business is not interested in how well my model is performing, but in how much money how less work people have to do in this process. So if everything works as it should, we should see a systematic decrease of the time that people spend in classifying emails. So we have the notification, we have the times, so make some sort of feature engineering there, so data augmentation or whatever you want to call it. So add some other data, like the duration of the mail classification process that is happening on the other side, and send it to some other database like Elasticsearch that is provided with colors here, like Kibana, that is this application where you can plot things in real time, because this happens in real time, this happens in real time, this is very fast and everything happens in real time, and you see plots in real time. Plots like how many emails I'm working with, divided by inbox, divided by the person that is working. So if we need to know if there are some group of people that is using this tool in the right way or in the wrong way, we need to do who is classifying that email, but the company software knows. So in the notification, it can just send us who is classifying that email, who pressed the OK button. And at least the team, okay, the team that pressed the OK button. Or here, if you remember, we said that we pre-selected the answer if the model is confident enough, so we can see how many times we were confident enough. So how many times the answer was pre-selected for people. And most importantly, for the business at least, is the times they need to classify this, to classify emails and for the entire classification process. So, in business words, our results, we were able to measure the systematic decrease of times given by our tool, because even though teams started at different times, all this notification and monitoring part was up at the first deploy, so that at the very from the first moment we could measure the success of this stuff. And what we saw is that depending on teams, but improvement went from 15 to 30% of the time. Yes, and another thing that I think was a very good result is that now the full email process is data driven. Like I follow the data from the end from end to end, and I can add more things if I want in a very easy way. Okay, we are really at the end, so conclusions. We learned that the question, how will people use whatever I'm building in production, is a fundamental question, and you may have, of course, learned about the standard data science workflow, where there's the exploratory part, talk with the business, exploratory part, train, test, split, train the model, validate the model, deploy. But actually the real job starts after the first deploy, and there you really learned something new, because you connect to the data generation process of your problem. And also the constraints that a production environment pushes to you, like time, availability, scalability, can be exploited scientifically to build more stuff, like that having this sort of impossibility to build monitoring on the same machines where the application is running. Actually, with this decoupling, now on the other side, we are completely free of to build something new there. So actually taking part of the full process from the very beginning, of course, that is covered. Yes, from the very beginning, I mean, just make the project to the very end. So put your hands in production. In my opinion, actually opens up a lot of opportunities. And yes, that's it. Oh yes, we're fine. So if you are a Python developer or a C# developer and you're interested, yes, let's chat or have, yes, just come to me and we'll talk about this. And yes, that's it. Thank you. I have been too fast. No, it's perfect. Yeah, questions? Yeah, please.
Well, I have some questions.
Yeah, sure.
First of all, well, when you were splitting the training, the predict, and the model,
Yep.
well, the part, you were actually building the feature store, right?
Mm-hmm.
Because you're embedding actually features that then you have to give to the model.
Mm-hmm.
Have you thought about deploying separately the feature store from the model itself?
With separately, you mean on different places that
Different
communicate?
machines, different places, different requirements.
Okay,
different
okay. I'm not sure, I mean, I'm not aware at the moment of the improvements this would give. Probably, again, more scalability or more, I don't know.
Well, for example, you can build more models. You can have one feature store
Mm-hmm.
that usually acts like a sort of mega singleton, right?
Yeah.
And you can have different models, so you can have an ensemble of models on the prediction part. And also, well, because that's your data set.
Yeah.
Probably when things start working well, people will ask more things from you on the same data set. So you can reuse the same features
I see your point.
and build something.
That's very
For
interesting.
example, in Uber, they have this huge feature store from which they pick up features for many different applications.
Yeah, that's very interesting. We didn't do that, but yeah, thank you for the comment. What I think is that it can open up more. I mean, a lot of opportunities for improvement, but also you will need to face some other stuff like then if you want to do at predict time the same process you did at training time, so actually you need to communicate between the prediction part and the feature storage part very fast,
Yeah.
for example, because you are summing up with network time in something that happens in this case just in memory. So yes, it could be, but probably you need to compensate somewhere else, or I don't know. Yeah.
And, well, the
Yeah.
second question
Please.
was about in the output.
Yep.
You gave to the user the selection.
Yep.
Right. But did you think about adding some explanatory part like shop values in your email?
No, actually no, because the point here is that about efficiency, meaning that this process is really heavy on people, and and the value of the sorting part is very small. I mean, people are doing this as part of their job, but their job is something else. They need to do this to start working. So the work happens after all this part. So actually the point was be as light in meaning of in the interface and as fast as possible, because this job must end up very soon. So whatever analysis you want to do on prediction, do it somewhere else, not there for the people that are working on email classification.
But with shop, you might, or line, whatever, you
Yep.
might be able to add highlight to the important word in the text, so people
That's
don't
true.
have to read the emails.
That's true. Yes, that's completely true. Yes, very good idea. We didn't do that. No, we didn't do that, but it's true. What we discovered actually analyzing the different times of the full process of sorting emails is that with this we completely we almost make to zero the classification time and the reading of email part. All the time that we couldn't decrease actually was time spent by the people on something else with the data that was in the email, like the number of some mortgage somewhere that they need to check on some other software while the email is there, so before pressing the OK button. So yes, they could be useful, but probably they already know about the email. So all the other time that we should decrease is something that we cannot decrease in this way. We need something else. Yeah, but thank you.
No, because in that case your increase is not 30%, it's 100%.
Yes,
You don't have to do that.
that's exactly the point. Yeah.
So you have to be less sharp.
Yeah. So the reason why it was 30 and not 100 is exactly that the other 70% is not reading the email.
Great.
It's working on the email. Other question?
I have one.
Yeah.
So when you added the proxy here, did it affect the latency time?
No. No way.
So it's the same.
I mean, HTTP is sort of okay. It's sort of magical for me, but it's very well built, meaning that it's sort of nanoseconds between the other, especially if they are in the same network. I mean, of course, if you put this in some network and there's a firewall, this in another network, and then there's a firewall here, then of course something bad could happen. But if your full application is in the same network, they communicate very fast. So the answer is no. We didn't notice any difference. Yeah.
Do you have units with attachment also?
Very good. Yes, there are lots of attachments. We actually, one of the features that helped here was the name of attachments that we give to the network. So yes, I was very sketchy on some things, sloppy on some details. We added some more features knowing the process, but we didn't add the image classification part that you may wonder about. It's one of the points that could actually increase even more the accuracy, but it is another story, of course. We would not be as fast as we are, and so on. So we are working on document classifications, but not this project. It's not so. It's not so important as we in that part, in the part of sorting the emails. Well, yeah.
One more question. So not about the details of the model, just out of curiosity.
Yeah,
You said
sure.
you needed it for yesterday.
Yeah.
So setting up all together, how much did it take you?
Okay. For the very first, when we, okay, excluding the exploratory part, like what are emails for us, so excluding this part to be in production with this, counting that we already had the deployment toy and so on, it's probably 1 month or 1 month and a half.
And
But then,
just you or like a team?
We were 1 plus half plus 3/4, so yes, 2 people and something.
Okay.
Okay.
Okay, food is coming.
Okay.
Thank you again.
Thank you.